A glass plate photograph rests inside a wooden drawer in a provincial survey office. The edges of the plate are chipped. The emulsion has faded into a pale brown haze, but the image itself remains sharp enough to disturb the eye. A group of men stands on what appears to be the top of a mountain. Their boots rest on bare stone. Their instruments face the horizon. Behind them, the land ends in a perfectly straight line. No broken ridges, no scattered peaks, just a wide, level surface suspended above empty air, as if the summit had been planed flat and left unfinished. The mountain does not look worn. It looks completed. The official explanation is familiar and widely accepted. Mountains rise through tectonic forces, then erode through wind, water, and time. Hard rock layers resist weathering while softer layers crumble away. Rivers carve valleys. Ice fractures cliffs. Sediment settles into basins. Over millions of years, irregular landscapes slowly transform into plateaus and mesas. Geology describes this process with confidence. The timeline is measured in epochs. The mechanism is gradual. The outcome is natural. That explanation accounts for many landscapes. It explains river canyons and rolling hills. It explains why valleys deepen and slopes soften. It explains why sedimentary layers form horizontal bands across cliffs. But there are features scattered across the planet that don't fully align with that narrative. There are summits that remain strikingly level across enormous distances. There are cliffs that descend in near vertical planes without gradual transition. There are mountain tops that appear less eroded than interrupted, yet the shapes feel intentional. The geometry feels controlled. There is another possibility, not a claim of lost civilizations or forbidden machines, but a more restrained hypothesis rooted in physical observation. The idea is that many flat-top mountains may represent the remnants of surfaces that were once part of larger, continuous layers of terrain that were removed or lowered by forces more abrupt than slow erosion. A leveling event, a removal event, a cutting event in the geological sense. Not necessarily a single moment, not necessarily a single cause, but an event large enough to leave behind consistent plains where peaks might have stood. Start with measurements. Survey data collected across the 19th and 20th centuries reveals clusters of flat-top mountains sharing similar elevations relative to surrounding basins. In the American Southwest, mesas often align within narrow vertical ranges despite being separated by long distances. Comparable elevation bands appear in parts of southern Africa, Central Australia, and western India. Independent survey teams, working decades apart with different instruments, recorded nearly identical height patterns. These are not identical mountains, but their final surfaces sit at similar levels, as though they once belonged to a broader structure that no longer exists. Old maps reinforce the observation. Early cartographers frequently drew plateaus as continuous terraces stretching across regions that are now fragmented by valleys and escarpments. In 19th century atlases of South America, entire highland systems were labeled as uniform tables, before detailed surveys subdivided them into isolated formations. As the same pattern appears in the colonial maps of Africa and Asia, the language used in those documents is revealing. Surveyors described broken tables, fragments of former surfaces, say sections of land that appeared to have been separated rather than formed independently. Photographs taken before large-scale industrial development add another layer of evidence. Early aerial images show plateaus with remarkably smooth summits extending for kilometers without significant variation in height. modern elevation scans confirm those impressions. Laser mapping technology reveals that some flat-top mountains maintain differences of only a few meters across areas large enough to hold entire towns. Nature can create flat ground. But sustaining that level of uniformity across such distances requires conditions that are unusually stable. It requires an initial plane. The mainstream explanation addresses this stability through the concept of caprock. Resistant rock layers protect underlying strata from erosion, preserving a flat surface while surrounding material disappears. In regions where climate remains relatively consistent and tectonic activity is limited, caprock can maintain broad plateaus for millions of years. That explanation is supported by laboratory studies and field observations. It is grounded in measurable physics. It deserves respect. But caprock explains preservation. It does not explain origin. Where did the original plane come from before erosion began? What created the level surface that caprock now protects? Look closely at the edges of these formations. A cliff faces on many flat-top mountains descend in abrupt vertical walls that show little rounding or gradual slope. The transition from horizontal summit to vertical drop often occurs within a narrow margin, producing angles that resemble structural breaks rather than slow weathering. In engineering terms, the geometry resembles a shear boundary, a surface produced by separation, not by decay. Geological field measurements reveal another detail. Cliff retreat in many plateau regions occurs at extremely slow rates, sometimes measured in centimeters per century. At that pace, creating a summit several kilometers wide through erosion alone would require an initial surface that was already level across that distance. Otherwise, the retreating edges would expose uneven terrain beneath. Instead, the surface remains flat. The plateau persists, and the pattern widens when examined across continents. In South America, the Tepuy formations of the Guyana highlands rise as isolated towers above dense forest. Their summits form broad stone tables, often surrounded by sheer cliffs. In southern Africa, escarpments along the Drakensberg Range display similar flat ridges extending across hundreds of kilometers. In India, sections of the Deccan Plateau maintain consistent elevations despite variations in rock composition and geological history. Different climates, different rock types, the same geometry. This repetition changes the scale of the question. A single, flat summit then can be explained by local erosion. 2 or 3 can be explained by coincidence. But when similar forms appear on multiple continents, the explanation must account for consistency. The pattern repeats, as the pattern does not disappear. Historical engineering records offer additional clues. Mining documents from the 19th century often describe removing layers of rock from surfaces that were already level. Engineers referred to these surfaces as natural floors or benches. Reports from coal and mineral operations describe horizontal seams extending across wide regions with minimal variation in elevation. Workers did not create those surfaces. They exposed them. Infrastructure planning provides another line of evidence. Railway construction in the late 19th and early 20th centuries frequently followed plateau routes because the terrain required minimal grading. Surveyors documented long stretches of elevated land where tracks could be laid without extensive earth moving. In several regions, engineers described plateau corridors as ready-made pathways across difficult terrain. Stable ground, predictable slopes, reliable foundations. This convenience raises an uncomfortable possibility. If plateaus formed solely through slow erosion, why do so many of them appear ideally suited for transportation, settlement, and agriculture? Why do they function as natural platforms for human activity across widely separated regions? The record shows a pattern in timing. Major plateau regions often became centers of development soon after systematic surveys were completed in the 19th century. Governments mapped elevations, classified land, and established administrative boundaries. Within decades, towns appeared along plateau edges, and trade routes followed the same level corridors. The land did not change, but the understanding of the land changed. Institutional records reveal how scientific categories evolved during that period. As geology became formalized as an academic discipline, terminology standardized the description of landscapes. Plateaus were defined as erosional remnants. Mesas were categorized as isolated tablelands. These definitions simplified mapping and education, making complex terrain easier to classify and communicate. The system favored clarity. The system favored consistency. The system favored established explanations. This process does not imply deliberate concealment. It reflects the natural behavior of institutions. Scientific frameworks stabilize knowledge. Once a model becomes widely accepted, new observations are interpreted within that model. Funding supports research that reinforces existing theory. Textbooks transmit those ideas to new generations. Over time, the explanation becomes part of professional identity. Revision becomes difficult. Questions become rare. Yet, anomalies continue to appear in the data. Satellite surveys have identified clusters of flat-top mountains arranged along nearly straight lines that extend for hundreds of kilometers. These alignments do not correspond to known river systems or fault lines. They resemble boundaries between large sections of terrain that may have once shared a common surface. Separated segments, shared direction. Hydrology provides another observation. On several plateaus, water flows across the summit without carving deep channels. Drainage patterns often run parallel to the edges rather than cutting directly downward. Sediment accumulates at the margins instead of eroding the center. Yet the system stabilizes itself. The surface endures. There is also the question of missing material. If erosion carved these plateaus from higher mountains, enormous volumes of rock must have been removed. In many regions, nearby basins contain less sediment than expected from such large-scale removal. Geologists propose that ancient rivers carried the material far from its source, dispersing it across distant plains or ocean floors. That explanation is plausible. But the distribution of sediment remains uneven. The accounting is incomplete. Modern technology has sharpened the picture. High-resolution elevation models show that many plateau edges maintain remarkably consistent slopes. The angles repeat across regions separated by thousands of kilometers. In engineering, repeating angles often indicate standardized forces acting on similar materials. In natural systems, repetition suggests shared conditions. Either way, the geometry invites scrutiny. Policy decisions reinforce the perception of stability. 20th century land surveys frequently classified plateau regions as structurally reliable terrain suitable for major infrastructure. Roads, dams, communication lines, and military installations were built on these surfaces because engineers trusted them to remain level over time. They treated the plateau as a foundation, not as a fragile remnant. Economic behavior followed the same logic. Mining companies favored flat-top mountains because heavy equipment could operate safely on wide, stable surfaces. At large scale, excavation removed millions of tons of rock while leaving the underlying structure intact. The terrain behaved predictably, supporting machinery and transport without sudden collapse. The geometry proved dependable. Some researchers have begun to reconsider the origin of these surfaces from a broader geological perspective. They examine the possibility that ancient environmental conditions produced widespread leveling events through mechanisms more abrupt than gradual erosion, massive flooding, chemical weathering under different atmospheric compositions, or shifts in crustal stability could have created large planar surfaces before the modern landscape formed. These proposals remain controversial, but they are grounded in measurable observations rather than speculation. What matters is not the label attached to the process, but what matters is the evidence preserved in stone. The stone remembers. Rock layers record pressure, temperature, and movement across immense spans of time. They preserve fractures, deposits, and erosion marks that can be measured with modern instruments. These records do not adapt to theory. They remain. In several plateau regions, drilling operations have uncovered buried soils and organic material beneath the upper rock layers. These findings suggest that the present surface once existed at ground level under different environmental conditions before being covered or altered by later geological activity. A surface can be older than the mountain surrounding it. The record is still there. As the investigation widens, the focus shifts from individual formations to the global landscape. Flat-top mountains appear in deserts, forests, and coastal regions. They endure through earthquakes, storms, and climate shifts. Their geometry persists even as surrounding terrain changes. They remain level. They remain consistent. The pattern repeats. It is entirely possible that slow erosion created many of these forms. Geological time is vast, and natural forces can produce remarkable symmetry. But it is also possible that some plateau surfaces represent the remnants of processes that operated more rapidly than modern models typically assume. Processes that reshaped terrain on continental scales. Processes that removed material instead of gradually wearing it away. If such events occurred, they would not necessarily leave dramatic scars. There might be no single crater. No obvious boundary, only landscapes that appear slightly too regular to ignore, slightly too precise to dismiss. Institutions rarely revisit settled conclusions without strong incentive. Research funding follows established priorities. Academic departments teach accepted frameworks. Government surveys focus on practical outcomes. Stability becomes the default position. Over time, unanswered questions fade into the background. But physical evidence does not vanish. Measurements remain in archives. Maps preserve contours drawn by earlier observers. Photographs capture landscapes before modern development altered their shape. Satellite data accumulates year after year, revealing patterns that previous generations could not see. Evidence grows quietly. Return to the old photograph of the surveyors on the flat summit. They are not arguing about theory. They are measuring the ground beneath their feet. Yet their instruments record angles and distances with precision. Their notebooks preserve numbers that remain accurate long after the men themselves have disappeared. The data remains. The geometry remains. Mountain summits around the world share strikingly similar flat surfaces. These formations appear in different climates, different rock types, and different historical settings. The explanation for their existence has changed over time, but the shapes themselves have not. What changed was the interpretation. The real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.